Okie dokie. So we make sure that's in there good and tight. Okay. So as you noticed, when the heck did I get your project to you? Yesterday or the day before? I don't remember. Saturday or Sunday? Saturday? Wow. How about that? I did well. You are working on that. I will open up Module 4 probably tonight. Would have done it this morning, but I was trying to get stats opened up and going on theirs. And so I'll have homework due dates, all that kind of stuff on there. Quiz, what I'll probably do with the quiz is actually make this a written one. So I'll post a PDF under the quiz stuff and have you just kind of do it like homework. Okay, I mean, it's a quiz, but you'll do it like homework. It'll have a relatively short turnaround time on it, but I'll give you a couple days to get that in. I'll still give you a second chance on it. Okay, so it'll be a 2-time quiz, so I'll have to get those back to you and give you another chance at it. But we'll try to make that all happen relatively quickly. And let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. That's right. Okay. Any questions on anything right now? Guess that's a no. All right, well, we are starting into chapter 3 with application. Oh yeah, boy, I tell you, it's amazing. You drop the chalk and, so we're starting in on applications of differentiation, and it begins with extrema. Okay, so maximums and minimums of functions. And yeah, that actually turns out to be a major application of calculus, is just helping us find, what's the best answer. Okay, and it the thing is, if you could graph the situation so that it's kind of unfortunate, really, I guess, that we're just looking at functions of a single variable. So see, we could go graph, anything we want to work with, we could just go graph it in Desmos. If somebody said, oh, here's a function, what's its maximum? I'll go to Desmos and look, right? I mean, I just plug it in and there, and zoom out and zoom in, and I could probably get a perfectly good answer almost 100% of the time of any real function that anybody really cares about. Okay, so that's sort of unfortunate in a way, because what we do when we look at the extrema, in this chapter, we're looking at ways to know without seeing the picture. Okay, that's kind of the whole idea, is how do we know, sort of by being inspired by the picture, how do we know where a maximum or a minimum of a function occurs, right, but without seeing the picture? Okay, and the reason you care about that is you may need to, in real life, you often need to maximize something with maybe as few as half a dozen variables. Okay, but as soon as you get to a function of 3 variables, you aren't going to draw it. Okay, and even a function of 2 variables, drawing, those 3D renderings, it's actually kind of hard to see what's going on at times. And so that's where this is unfortunate, because kind of everything we do, you can see it. And you don't really need calculus to answer a lot of these questions, okay, because they're just a function of 1 variable. Okay, but what you have to imagine is, what's good about this is everything you do algebraically, you can actually look at on a picture, a graph, and see exactly how your algebra translates into the picture. And I think that's what's very important, is realizing that so that you can translate between these 2 things, okay, the algebra and the graphics, so that if you're in a situation where, depending on what you go into later on, if you're, if you do some sort of science, there is a good chance at some point you will want to optimize stuff. And I can give you one example. I'll probably give it to you later, but I can give you one example of a case where I actually just used the basics here for a function of 1 variable and made a scientist, a food scientist, very, very happy, okay, because he was using numerical stuff. He was looking at the graph, basically, and I did it using the algebra, and it made him so happy I got my name on a paper just because I took the derivative and set it equal to 0. Okay, that's what we kind of do in this case. So with that, this is 3.1, and we say Extrema. Okay, so that's just our maximums and minimums on an interval. Okay. Now, so they go into the definition. So algebraically, we can talk about a maximum and a minimum, but I think it's also very important in pictures, right? So that spot there looks a lot like a maximum. Okay. So there's our maximum. And if I'm looking at something like this, then there's a minimum. And as we look at those, sort of what you want to do is think about, well, yeah, it's obvious to me in the picture, oh yeah, that's a maximum. Peak, mountain peak, something like that. But what you want to start doing is thinking about, well, how do I know that? And what I'm seeing is that if I throw an axis system on here, right? So if I throw an axis system on there, what I'm noticing is if this is a function, I'm noticing that all these values of my function are smaller than that value. And similarly here, all my values of this function are greater than that one. So if I'm looking on a particular interval, so that's what they're talking about, they say on an interval. So here's my interval, and they name it an interval I. So so let's see, let me get it the way they, so they say, let f be defined on an interval I. Okay, so that's just some interval. Then, and then, oops, I didn't want a period there yet, containing C. Okay, so, C is just that X value there underneath the minimum or the maximum in this definition. And then they say, well, one, f of C is a minimum. They do minimum first, I guess. Minimum of f on I. Okay, if, and notice they say f of C is less than or equal to f of x. Okay, so you can have more than one. So you could have sort of two peaks at the same height. But it's less than or equal to f of x for all x in I, in that interval. And then similarly, so f of C is a maximum of f on I if f of C is greater than or equal to f of x for all x in I. Okay, so there's our nice mathy formal definitions. But all they're really saying is what we see here. That's the nice thing about the graphical stuff. That is a great thing about working with just a single variable is, I can see stuff here and draw stuff and so forth very, very easily and see it very well. But the mathematics tends to look much more formal. Okay, so a big thing here. So here's a big theorem, big theorem. All right. So our extreme value theorem. Okay, so for our extreme value theorem, this is where continuity comes in. So why do we study a little bit? I mean, we don't do a lot with continuity, but we brought up this idea of what's a continuous function, what does it mean to be continuous? Well, why? Why? Well, it turns out just knowing you have a continuous function can help you quite a bit. So, for instance, you cannot, if you have a discontinuity, you cannot have a derivative there. Oh, well, that's kind of good to know. Similarly, though, if f of x is continuous on the closed interval I don't remember if they call it I again or AB or what. Oh, interval AB. So they call it AB. So on the closed interval AB, then f has a maximum and a minimum on AB, or at a couple values there in AB, another way to say it. So that's kind of a big deal, right? And if you just play with it, it actually is pretty intuitive that ought to be true. Okay. checking that. This thing came out the other day, so. Okay, so it seems reasonable that it ought to be true. You know, if I just go here and I take some interval from A to B, and you know, I'll start the function here maybe and stop the function there. If I make it continuous, you know, I could do all sorts of things with it. Okay, but if it's continuous and you look at that, you say, well, yeah, it does seem like, you know, at some spot, in this case, there seems to be where the maximum occurs. And looking here, it looks like here's where the minimum occurs. So, you know, there's our minimum and there's our maximum. Right, but if I do it continuous, do a continuous function, I can't see how I would do it any other way than to achieve a maximum and a minimum somewhere on there. Now, if it's not a closed interval, you know, so it says closed interval and continuous. So the continuity part seems reasonable, right? If I get rid of continuity, so if I get rid of the continuity part on here, then here's my closed interval. There's A, there's B. How could I have it not have a maximum? Well, suppose I just do something simple like go up here, have an open circle, and then here, and come down like that. So F is defined everywhere on AB. Okay? And it does have a minimum, maybe here or there, one of those two. But it doesn't have a maximum. Okay? Because, you see, having that open circle there, I can, you know, if this is, say, the value C, then as I move towards C from the left, I keep getting a bigger and bigger and bigger number. But I never reach a biggest number. Okay? Because, well, you know, if I'm at C minus 0.001, okay, well, that will have some function value there. But then if I go closer to C than that, like C minus 0.0001 or something, well, that'll be a bigger value, it looks like, according to this picture. So if I don't have continuity, it is possible that I don't achieve a maximum. Now, the function is bounded. Okay, that's something we, you know, that's a term in mathematics. It's bounded, right? It's no bigger than whatever that value would be there at that open circle. But it doesn't have a maximum. Okay? So we definitely need continuity, because if we don't have it, I can come up with an example pretty simply where we don't have a maximum. And then if it's an open interval, well, let's just take like 1 over x, right? So if I look at something like 1 over x from 0 to 1, say, is my interval, well, there again, I happen to pick something that had a minimum, but again, it has no maximum. Okay, so it's continuous on the whole interval that I'm talking about, the open interval from 0 to 1. And I could, well, this could be the half open interval, open at 0, closed at 1. But you see, as we go up, no matter how close we get to 0, we could get a bigger number, so we have no maximum. Okay, so we do need both of these things. We need a closed interval, and we need continuity. Now, if it's continuous on that closed interval, then it's also defined everywhere. So certainly we need it defined everywhere on our interval. But if we have continuity, it is defined then. So. Okay, so that's our extreme value theorem. Any questions about that at this point? No? Are you all too old for Mr. Rogers? Or something like that? Or too young for, I guess it'd be too young for Mr. Rogers, because Mr. Rogers' Neighborhood started sometime when I was quite young.
The horse.
Isn't that Wilbur and Mr. Ed talking to a horse? Did he talk? I don't. He had puppets. He had a very annoying cat puppet that went meow 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 meow. No, not Mr. Rogers.
Yes, we're too.
Yeah, somebody knows of Mr. Rogers. Okay, you know. Fred Rogers, awesome person, the best I can tell. I didn't actually know him, but yeah, Mr. Rogers' Neighborhood. Eddie Murphy used to make fun of it on Saturday Night Live, but again, that would have been way before your time. Maybe you've seen reruns, I don't know. But why am I talking about Mr. Rogers? Because of the neighborhood. So we're going to talk about neighborhoods here. And so often what we're looking for in order to find our maximum, again, you know, so here's an interval, and I would really like to find that spot right there. Okay, because that's a maximum. I'm trying to maximize something. Well, so how, you know, again, we noticed that every value was smaller than that on that interval. But the question is, sort of, what else, how do I know, or what else am I noticing, or that I could use possibly to realize I'm at the top? The slope equals 0. I didn't even have to pay you for that. That's good. So, as long as I have a differentiable function, okay, as long as I have a differentiable function, when I hit the top, the slope there of that tangent line is 0. Right? So m equals 0. Or, you know, if we call this c, f prime of c is equal to 0. And so that may be a way I can kind of check. I can get candidates. Now, okay, so that's one way. Now, it's not a surefire way. Okay, just because the slope is 0 certainly doesn't mean it's a maximum, right? Because, well, it could be a minimum. So I could have the same sort of thing. And, you know, there, f prime at c is equal to 0. So there's my c, and there's b, I guess, and a. Okay, so it could be a minimum. But if you just take something like y equal x cubed, you could also have, now this isn't y equal x cubed, but same idea, is you might have a situation like that, where that's a, that's b, and right there at c, you have a horizontal tangent line. So just because the derivative is 0 doesn't mean I have either a maximum nor a minimum. Might be, well, what we'll end up calling an inflection point. So it might be that case. But it certainly narrows it down. Now, but the first thing I drew, though, other cases, you have something like that. a nice peak there. That's what I drew the first time. So there's A, there's B, there's my C, Y and X. In this case, though, if that comes to a point like that, right, it doesn't have a derivative. Okay, because the limit coming in this side is going to be different than the limit coming in from that side of those tangent lines. So if it's, you know, those are relatively straight lines. Suppose they're supposed to be straight lines, right? That's a corner. And so the derivative might be undefined. And so here, f prime of c is undefined. So that's another possibility. Again, it's not a surefire thing because I can do all sorts of things to make it undefined, but could be a minimum again. It could be a discontinuity, right? The derivative is definitely not defined there. And so as I look at this, though, it really comes down to two candidates, okay? I can look for, now, here, the names of these things, they might, you know, this might be the maximum. That might be the minimum of that whole function. But what we know for sure is at least in a neighborhood. Okay, so in a neighborhood. And all a neighborhood of a point means, well, actually it's usually a neighborhood of the x value. So a neighborhood of this x value just means some small interval containing that x value. Now, small. How small? As small as it needs to be. In this case, heck, the interval could be as big as this from A to B. But if I made it more jagged or something like that, I might have to have smaller intervals. Okay, so when we talk about relative extrema, so here we have, okay, relative extrema. So that means at least in their little neighborhood, their little pond, they're the biggest fish or the smallest fish in their little pond. Okay? So there might be a bigger fish or a smaller fish out there, but at least in their little spot, their little neck of the woods, they are the extreme place. Okay? So I can look for relative extrema where f prime of x is equal to 0 and f prime of x is undefined. That's where I'm going to look. Now you see, I can look for that without actually looking at the graph if I have an algebraic representation. See, so this is the big deal, sort of, is that all of a sudden I can do it with my eyes shut. Well, probably not really with my eyes shut, because then I'd be writing all over the place. Right? Okay, but this idea that they introduce of relative extrema, they are just these local troughs or local peaks. Now, they could be a global extrema. That means the biggest everywhere, or the smallest everywhere. But right now, we're just interested in looking for these relative extrema. So where the derivative is 0, that kind of thing. Okay, and so if f prime of c is equal to 0, Make sure I don't knock that off. Okay. If f prime of c is equal to 0 or undefined, we call C a critical number. Okay? So if somebody starts talking about critical numbers, they are simply where, now this says where the first derivative is equal to 0 or undefined. But really, and I think, let me look at the book's specific definition here. Yeah, they only talk about it for that first derivative. Okay. However, actually, you can talk about the order of the critical number. And so, since this is the first derivative, I would call it a first order critical number. If I was doing the same thing with the second derivative, I would call it a second order critical number, and so on. So at this point, we're just talking about the first derivative, so they don't really feel a need to talk about first order, second order, that kind of thing. But these are first order critical points. And so we're sort of ready, more or less, to try to find minimums and maximums on a closed interval. Okay, because we certainly know how to evaluate the function at a point, I guess, or at least theoretically we know how to do that. And then we've got a tool now to look for relative mins and maxes. And so, for example, their example number 2 okay, their example 2 is they say, well, let's find Extrema for f of x equals x 3x to the fourth minus 4x cubed, like that, okay, on the interval minus 1 to 2. So on minus 1 to 2. Okay, so they mentioned some steps. Yeah, and I would say, I'm not real big on sort of algorithmic kinds of things. For instance, there are 4 steps that, there was a very good mathematician, great mathematician named Polya, and he tried to help people, and he said, well, there are 4 steps to problem solving. Well, I get it, but at the same time, as soon as you say there are 4 steps to problem solving, it's kind of like you don't get it. Okay? Because real problem solving is not an algorithm. Okay? You can't just go, oh, start here and do these steps and get it done. I mean, at some point you can. So, for instance, with the quadratic formula, something like that. Oh, okay, yes, you line up everything to get your A, B, and C, and that kind of stuff. Sure, that becomes algorithmic, but really you're not problem solving anymore. You could just get technology to do it for you. Okay, so real problem solving, there are guides to what things you ought to do, like make sure you have the problem well defined, that kind of thing. but in the end, it's not an algorithmic process. Well, here, yeah, I would call these more rules of thumb guidelines and so forth. I wouldn't say, oh yeah, you follow this every single time and everything will be perfect. For a lot of our book problems, yeah, probably the case. Okay, so step one, they suggest, is, well, find your critical values. Okay? Find critical numbers. And in many ways, this is a bit algorithmic because actually what we like to do is be able to teach computers to do this for us. Okay, and that's the power of calculus is, well, we use the theorems and so forth in calculus, and then we can tell a computer to go do this. Oh, that's awesome, right? And then it just gets answers for us. So find critical numbers. Well, we need to look for where the derivative is 0 or undefined. Now, often you can forget about the undefined part. I mean, I should say, not that you can, you will forget about the undefined part, but you shouldn't. In this case, though, I have a really nice polynomial. The derivative's defined everywhere. This is a really nice function, okay? I'm not going to have a problem, right? If I'm dividing by 0, then, yeah, I could have a problem, right? If I am taking square roots and things like that, I could have a problem. When I've got a nice function like this, I don't expect there to be a problem with the derivative. So here, I'm going to first take the derivative. Power rules on those with the constants, so I get 12x cubed there minus 12x squared there. And then I'm just going to set it equal to 0. Now I'm going to solve for x. Okay, so I have 12x cubed minus 12x squared equals 0. Well, divide everything by 12 and factor an x squared out. So I have x squared times x minus 1 is equal to 0. And so from that, I've got two possibilities. X equals 0 or x equals 1. And in a way here, this is typically how we write answers to an equation like that. But in our context, really, I could say and. Okay, because what I'm asking for is where the derivative is 0. Well, it's 0 at x equals 0 and at x equals 1. Okay, so there, I've got my critical numbers. And so now it says evaluate f at each critical number. Okay? So, to evaluate f. Now, this is, it's possible that you might not be able to evaluate f, although I think on all these problems they're going to say it's continuous. They're just going to give you a continuous function. So the derivative may have issues, but the function itself, I think, is going to be continuous, and therefore you should be able to evaluate f at any of the critical numbers you come up with. So evaluate f. Well, f of 0 equals 0, and f of 1 is equal to negative 1. So 3 times 1 minus 4 times 1, negative 1. Okay, so we did that. Now, so, well, if 0 is an extrema, I'm going to guess it would be a relative maximum. And if 1 is an extrema, I would guess it's going to be a relative minimum. Just because the one's bigger, the value's bigger for the one than the other. Okay, so then it says evaluate each endpoint. Okay, so, whoops, 3. Evaluate endpoints. Now, why are we doing that? Well, because the question is, says find the extrema. Okay, it didn't say find the relative extrema. It said find the extrema. And that means I'm looking for the maximum and the minimum. Now, I say the, I mean, it could occur in more than one place. But I'm looking for the maximum, the minimum on each of these. So evaluate at the endpoints. So I need f of -1 is equal to 3 times -1 to the 4th minus 4 times -1 cubed. Well, that's 3 plus 4, okay, because I get negative and a negative. So I get 7 there. And then f of 2 is equal to 3 times 2 to the 4th minus 4 times 2 cubed. So 2 to the 4th, 16. So 48 minus 8 here, 32 is equal to 16. Okay, so we found candidates inside the interval, and then we looked at the endpoints of the interval, and it says the least of these values is the minimum, the greatest the maximum. So that's their step 4. Okay, least. Now, the least of what value? Well, all the values of f that I came up with. So least looks to be f of 1 equals -1. Okay, so that's our least. And so the minimum is -1. The x value at where that occurs is at 1. So, those are just, somebody says find the minimum and you say x equals 1, well, you're wrong. That's where the minimum occurs, but the minimum is the value of f. Okay, so minimum is -1. Okay, and greatest, well, that looks to be our 16 if I did that right. So f of 2 equals 16, and so our max, or maximum, is 16. Okay, now I think looking at a continuous function and relative extrema and endpoints and so forth, what you want to do is convince yourself that that's all you need to look at on a closed interval. That's all that you need to do. So, our intuition, and this is where it's nice that we can draw these things. All right, so what do we have in this case? We had actually That was way up there at 16. We had here at 7, we were at this spot. Okay, now that spot's actually -1, so you know my axis isn't really in the right place, right? But and then we had some values that were 0 and negative down here. Okay, well, so we had to, where were those? At 0 and 1, right? So we had to hit 0 there, and we had to hit -1 here inside of this interval. So now, connect the dots with a continuous function. But you have to make sure the tangent line is horizontal at those two spots. Okay, so what might you do? Well, you might come down and say, oh yeah, okay, we'll put a minimum there, and put a minimum there, and go back up to there. No, wrong answer, right? Because we didn't have a maximum anywhere like that, right? We only had 2 critical points. So what had to have happened was this came down, flattened out, kind of like y = x cubed, then came back down here, and then went up like that. Okay? That's what our function must look like, more or less. It could have some wiggles in there or something, but none of those wiggles could be big enough to make a minimum or a maximum inside there anywhere, a relative min or max, because we only found those 2. Those were the only 2 possible places. And so when you start thinking about drawing anything, right, start here. Well, try to keep it a function, but you know, you get the idea, right? Where could there be maximums and minimums? Oh, at all these spots here. Well, maybe there. Nah, probably not. But there, and oops, that doesn't look much like a function. There we go. Right? We could get them at any of those spots or the endpoints, because the endpoints derivative may not be 0, right? Just like we had here. But try to draw anything continuous. Those would be our only choices. Oh, I could do that. Right? Oh, yeah. Well, endpoints, those are possibilities. And that relative maximum up there is a possibility. Okay, but nothing else is a possibility. And so, pretty much following those 4 steps does actually do it for us as long as we're on a closed interval. And that's what this this section is all about, is just closed intervals. Okay, questions about that? Anything on those? No? And what, we get done in a minute or 50 seconds or something like that, right? Okay. So we aren't going to really push 3.2 a lot. You'll have plenty of homework on it, you know, but as far as really pushing that for mastery and so forth, not so much worried about that. But then the rest, the 3.3, 3.4, that kind of stuff, and drawing. One of the things I'm going to work with you a lot on, I need to, I think I've actually made an interactive thing, but it's not posted yet, is drawing derivatives from the function. So basically you're not really given much information, but you're asked to draw the derivative from the function. or draw the function from the derivative, that kind of thing. I'm going to have you do a lot with that. I think that's an important thing to do, to get the graphical side of that down. And I'm not sure exactly when, but possibly as early as Friday, I will be posting a test. We'll have to take, we need to take tests at some point, a few of them. It'll be a take-home thing. You'll be able to use Desmos, that kind of thing on it. So possibly as early as Friday, more likely it'll be next week sometime, and I'll give you a couple days to work on it. And so what'll probably happen is we'll have class on Monday, and you'll be given the test later that day, and then it'll be due like Wednesday night or something like that. So you'll have maybe 48 hours-ish to work on it. Okay? All right, and I will see you on Thursday.